Let us consider a spring having spring constant K attached to a mass m. Let this be the spring and this is the mass attached to its end. Let the spring constant be K. Let the spring constant be is equal to K. So since this is the mass m, without any force acting on the mass, this will be its mean position. Clear? We can call that as x is equal to 0. We usually take the mean position to be the origin or the coordinate 0. Suppose when a force is applied to this spring, to this mass in the right direction, suppose we stretch this mass to this length and then we release, the spring starts to oscillate or the mass starts to oscillate about the mean position. So the two different positions on the spring are of the masses are, the two different positions of the mass are one at the extreme right and other at the extreme left. Let's draw that. So the spring will be stretched here or there will be an elongation in this spring. So the mass will be somewhere here. Clear? So let this point be the maximum elongation of the mass. So we call that as extreme position and we take x is equal to, at this position, x is equal to maximum displacement, maximum horizontal displacement or amplitude. Similarly, the mass will come to the mean position and it will go further because of the inertia. So the spring also gets compressed. So the mass will be somewhere around here. Clear? So these are the three different positions. Let's call that position x is equal to A. So these three are the different positions of the mass. One, it is at the equilibrium position or x is equal to 0, and other at the extreme ends. Since it is on the left, we can put a x is equal to minus a. Let m be the mass of the body attached. Let's call this point as O, this one as L, and this one as some m. Clear? So if we draw a straight line and represent these 3 points, this is our origin and this point is the L and this point is M. Clear? Here we know x is equal to 0. Here x is equal to A. See, this M0, L are the different positions of the masses in when the spring is elongated and when the spring is compressed. So this is equal to x is equal to minus A. And by the law of conservation of energy, let us assume a point, another point somewhere around here. That is a point B at a distance x units from the mean position. That is, if we take another position of the mass somewhere around here, let's call that point B and let that distance be x. We don't know where it is, but we only know the distance from the mean position is x. So we need to find the velocity of the mass at this point. So for that we are using the law of conservation of energy. And we know at every point, suppose every point the total energy remains same. That is, total energy at the mean position O is equal to, or total energy at the position L is equal to total energy at the position P. At every point, whether it is M, O, P or L, the total energy remains the same. Now let's take the position L. Here the spring is stretched to its maximum, which means x is maximum. That is, potential energy will be maximum here. Potential energy will be maximum here. So all of the energy is converted to potential energy, which means the kinetic energy must be zero here. Clear? So total energy at L, I mean the potential energy at L and the kinetic energy at L. So total energy at L, TE stands for total energy. Total energy. So total energy at L will be potential energy at L plus kinetic energy at L is equal to, here total energy at P is potential energy at P plus kinetic energy at P. Clear? So potential energy at L will be, we know the potential energy expression for potential energy is equal to half k x square. This is the expression for potential energy. Since x is equal to a, we can write potential energy at L is equal to half k a square plus kinetic energy at L is 0, at the position L is 0, is equal to potential energy at P. Potential energy at P we don't know, so we just write half k, the distance is x square, plus kinetic energy. You know the expression for kinetic energy, half mv square. Clear? So if you simplify this, you will get, that is half k a square, taking this term to the left, minus half k x square is equal to half mv square. So half k you can take out, a square minus x square is equal to half mv square. This 1 by 2 and 1 by 2 will get cancelled. So v square is equal to k by m a square minus x square, which means velocity at the point P, or velocity at any point of the motion of the spring, we have v equal to root of k by m times a square minus x square. So this is the expression for velocity at any point during the motion of the spring or during the oscillation of the spring. We will say that the spring is oscillating because it is oscillating about the mean position. It continuously changes its position horizontally. Clear? Now, let's look at the different cases of velocities at the different points. Suppose, let's take the case A. Case A, velocity at the extreme points. Velocity at the extreme points. And we know at extreme point means the position at M and L. We have at extreme position x is equal to a or x is equal to minus a. So velocity at extreme position, we write velocity at extreme is equal to root of k by m a square minus, it doesn't matter whether it is x is equal to minus a or x is equal to plus a. Anyway, the square of square of a square is equal to a square. Square of a or minus a is a square. So the value will be 0. So at extreme position, there is no velocity. Then what about the velocity at the mean position? Velocity at mean position. Velocity at mean position. Which means case B. Therefore, V is equal to, at mean position, you know x is equal to 0. At mean position, x is equal to 0. Therefore, V writes that as V origin, or velocity at the mean position, is equal to root of k by m a square minus 0 square. This will be root of k by m a square. Therefore, V0 is equal to k by m root of k by m times a. So this is the velocity at the mean position. Now let's take the third case, that we want to know at what point the kinetic energy is equal to the potential energy. So at what point during the motion of the mass or during the oscillation of the spring, the potential energy and kinetic energy are equal. For that, we have the expression for kinetic energy, half mv square is equal to half kx square. We also know half v is equal to, v is equal to k by m root of k by m a square minus x square. Clear? So v square will be k by m a square minus x square. This is v. So v square equal to k by m a square minus x square equal to half k x square. Cancel this half and half. This m and m will get cancelled. Also this k. Which means a square minus x square equal to x square. Which means 2x square equal to a square. Taking this x square to the right. That is x square equal to a square by 2, or x is equal to root of a square by 2, implies x is equal to a divided by root 2. So at the position x is equal to a by root 2, that is, if you take a distance x which is equal to a by maximum amplitude divided by root 2, then at this point or somewhere here, let's call that as point Q, here the potential energy and kinetic energy are equal. Clear?